Okay, let's look at another application problem that is a geometry-based problem, but it also combines our knowledge of circular sectors that we did earlier in the module. So let's take a look here. We've got an equilateral arch, which is drawn about an equilateral triangle, and the sides of the triangle are each 10. Okay, that means that the 10 is also the base AB of the arch. Okay, now an equilateral arch is this. It has a straight base, but then it's formed by two arcs meeting. So AC is an arc and BC is an arc, and they are equivalent in length. So if you want to think about the sides of the triangle AC and BC being shaped or bent outward into an arc length, you could think about it that way. Alright, so we're to calculate the total perimeter of the arch. The arch is in blue in the figure, and then we're to calculate the area. Now in order to do this, we need to remember how to get arc length, and we also need to remember that equilateral triangles are kind of special, because all of their sides are equal and all of their angles are equal. So each of these angles would be 60 degrees. Okay. Now, what does it take to get an arc length? And each of these have the same value. Okay, so I only need to do it once. Well, I'm going to shade over this so that you can see this with me. When you form the equilateral arch, contained in it will be two identical sectors, like so. So you've got sector ABC and you've got sector ABC if I go the other direction. So hopefully all of you are following me. There's two of these. They're just alike. So I only need to use one of them to get the arc length S. Alright, so looking at the sector I have, the first one I highlighted. Let's look at its components. Okay, remember these were the two sides of the triangle, here and here. And then this guy is 60 degrees. Now we know that to deal with sector formulas we have to convert our angles to radians. Okay, so let's remember our definition of radian measure was theta in radians is arc length divided by radius. So the radius times the angle in radians is the arc length. Okay, so in this case it means that our guy S is R times theta, which in this case is pi over 3 radians, and that's our arc length S. Okay, so our perimeter of our sector, and we do have the calc pad available here, so we can say it's the base 10 plus two guys, each of length S, so I could just go ahead and lump them together. 2 times 10 times pi over 3. Okay? Alright, now let's move on to the area. Okay, to get the area, you could take the area of the entire sector I just noted. I don't want to draw over this too much, but that would take care of all of this. But then I would still need this little missing piece off to the side. Well, the little missing piece, if you will, is the distance, and let's do another color here, this little piece, okay, between the area of the sector and the area of the equilateral triangle. Okay, so I could either look at this as I take two sectors, add them together, and subtract out the triangle because I would have counted it twice, or I can do one sector plus this little region. You can do it either way. So the area, remember, of a circular sector is 1/2 the radius squared times the angle in radians. Okay. And the area of the equilateral triangle, I could either do with the equilateral triangle's area formula from geometry, or I can do my side angle side area formula that we derived earlier. And if I do it in the side angle side manner, I would say 1/2 the product of two adjoined sides, so here and here, times the sine of the angle between them. Okay, now, but don't get confused. I could also have dropped a perpendicular and used right triangles in that manner to get the area of the equilateral triangles. There are a lot of ways I could approach this, but I love the side angle side area formula when we can use it. So you have to basically know a side, the angle in between, and the other side. Okay? All right, so knowing this, then we're basically going to, I'm going to do it the first way I mentioned. You're going to have the area of the sector plus the little missing piece that looks like a little piece of biscotti, okay, which is the area of the sector, again, minus the area of the triangle. I'll squeeze that in there. Okay, now, it is okay for this angle to be in degrees because it is being called upon by the sine function. But if you're using a sector formula where the angles are standing alone, they're just numbers. They need to be in radians. Okay? All right, so again, it was two sectors. If you do it that way, you've overlapped by one too many triangles, or you can look at it as I did the first time, the sector in yellow plus the little piece off to the side, which is obtained in this manner.